Okay, welcome back. Now I'm going to do a demo I'm calling string folding over a table. You could also call it rope folding over a table. So what I'm going to do is I'm going to take a string, put it over a table, then I'm going to put a portion of the string over the table, and that portion, let's call it X. And my first question is going to be, how much of that string should be hanging over the table in order for the string to start sliding and go fall off the table, basically. So what portion of the string, my second question is related to that. Once it starts sliding, then how many seconds will it take for it to completely come off the table? So how many seconds will it take? Just measure the length of my string, right? And then the next thing I'm going to measure the coefficient of static friction between my string and the table. So let's measure the length. Then I'll measure, this is 1 meter of the string. And then from there, I'll measure the rest of the string. And that's going to be 37 centimeters. So about 1.37 meters. 1 meter and 37 centimeters. So next I want to measure the coefficient of static friction. So what I will do is I will put it over the table. And I will incline the table so that the string is starts to slide. And then the point where it starts to slide, you have the normal force up like this, and then you have mg, and the friction force is equal to the maximum value that it could possibly be, mu Sn, right? And then this is the angle of inclination is theta, so we can break the forces into components, the weight. This component of the weight is mg sine theta, and then this component of the weight is mg cosine theta. So we can say mg sine of theta is equal to the force of static friction, the maximum value of the force of friction, mu Sn, and then the normal force is equal to mg cos theta. So we'll put that over here. N is equal to mg cos theta, and then we divide the two equations. That eliminates the normal force, and then the mg's cancel, and then we have tangent theta is mu s. So this is the best experimental way of measuring the coefficient of static friction between a block or a string or anything and another surface. Start to incline that surface until the string or block starts to slide. So let's perform that experiment. Okay, at that point the string is sliding. Let's measure the angle. 20 degrees, roughly 20 degrees is what caused it to start sliding. Okay, so then we can take the tangent of 20 degrees, 36. We can now estimate what the coefficient of kinetic friction is going to be. Usually the coefficient of kinetic friction is slightly smaller than coefficient of static friction, by maybe about 10 to 20%. 10 to 20% smaller than this. So that's going to mean the coefficient of kinetic friction is approximately 0.30, I can estimate. And then the coefficient of static friction experimental, we got 0.36. So now, in order to answer part A, we just need to know the coefficient of static friction, not the kinetic friction. Okay? So then, how are we going to solve that? We're going to say, okay, let the portion of the string lying over the table, let's call that a portion x, and then this portion of the string is L minus x, right? So then we're going to say the weight of this portion depends on the mass of that portion times gravity, right, mg. That weight is going to cause the string to want to go down, so we can say that's mg, and then that's going to equal to the force of friction mu Sn, right, mu Sn. And then the normal force on the string depends on the portion of the string that is sitting on the table, right? So then we can call that m prime, right? So then we have mg mu s, and then n is going to equal m prime g. M prime is the portion of the string that's lying on the table still. And then gravity cancels, right? Then I can define something known as linear mass density. Lambda is equal to the mass of the string over the total length of the string, right? So then I can say the little m is going to equal to the linear mass density of the string times the length of the hanging portion, right? So then I can put that here, lambda x. Then I can set this equal to mu s, and then my mu s was 0.36. And then the m prime will depend on the lambda times the portion that is sitting on the table, right? The linear mass density times the L minus x. And then what you will see is that the linear mass density will cancel. So what does that mean? That means the experiment doesn't depend on the density of that string. It could be a really thick string, it could be a huge rope, it could be a thin rope. As long as it has the same coefficient of friction, the answer will be the same, right? So then we can now put the length of the rope 1.37, right? So let's calculate this. 36 times 1.37, right? And then x is going to equal 0.36, right? So then we're going to say x is equal to 0.36 times 1.37 over 1.36. So let's calculate that. So 0.36 is the answer. What does that mean? That means if 36 centimeters is hanging from the end, it should start to fall. Or maybe, let's say more than 36, maybe 37 centimeters, right? So then what portion of it should be sitting on the table? L minus x. So then we can do 1.37 minus 0.36, 1.01. So about a meter of it, if a meter of it is sitting on the table or anything shorter than a meter, then it should start falling. So let's practice this, see if it works. And I'm going to have a meter of it here. So I have about a meter of it on the table, and you can see if I take it out, it's still not sliding. Well, there's a source of error in this lab that the coefficient of friction is not consistent across this table. Portions of the table might have a bigger coefficient of friction, so it's not coming out to be a perfect result. Let's see if 99 centimeters will do the trick. That doesn't do the trick either. How about 98, 94? How about 96 centimeters? No. Okay, I'm going to pull it 95. .95 centimeters. Also, there's another thing, that the edge of the table also has a friction due to the roughness of the table. So that's causing a bit of an error too. So let's see, 94, 93. Okay, so now I have it at 60 centimeters, and you can kind of see that it's starting to slide. 60 centimeters, right there. Okay, so it predicted that 1 meter has to be sitting on the table. When the length of the string on the table was 60 centimeters, then it slid, right? So that's going to be my percent error. Is going to be, the difference is going to be 0.4 divided by the theoretically predicted result 1, 40% off. So the fact that the coefficient of static friction is not consistent along the table, and the fact that the edge of the table provides more friction due to the sharpness of the table on the string, so that is giving an error. So I'm going to take my result from our actual setup. So we have 60 centimeters of the ruler of the string on the table, 60 centimeters. Okay, then we have the table like this, 60 meters. Then how much would we have hanging? 1.37 minus 0.60, so that would be 0.77. So 77 centimeters. So there's more of the string that's hanging down here, 0.77 meters that's hanging, that's going to cause it to accelerate, right? So now how do we do the equations of this, right? So we're going to say here the weight of this here, mg, and then this is going to be the coefficient of kinetic friction n, right? Once it starts sliding, you revert to coefficient of kinetic friction, 0.3, right? So then we're going to say mg is the force that's causing it to go down, minus the kinetic friction, na, mu kn is equal to ma. right? But the mass, notice, depends on how much of it is hanging. And as time goes on, more of it is going to be hanging. So the effective mass, the weight of the object that's causing it to go down, is increasing, this portion. So we're going to call this portion here x, right? How much of it is hanging. So we're going to say the m is equal to lambda xg, right? The linear mass density times x times g. And then n is going to be the portion that depends on the mass of the portion that's sitting down. So that's going to be lambda times L minus x g. So now what will this m equal? What is that m? Is that the portion that's just hanging? So this is kind of an interesting question, right? This m depends on the portion that's hanging, so lambda x. The normal force depends on the portion that's sitting, but which portion of the string is accelerating? We could say this is actually the total mass, right? This is the total mass. Why? Because the top portion of the string and the hanging portion, they're both accelerating at the same rate. So this is the total mass. So that's going to equal to the linear mass density of the string times the length of the string. And that's going to give you the acceleration. So notice the linear mass density of the string, again, does not matter. The lambda cancels out, right? And then we get an equation here. We can factor out the g. Then we get here x minus mu k L, right? Since I factored out the g, this one disappears. It goes outside. Then we have x minus mu k L, and then the minus mu k multiplies by the minus x. Then we get here positive mu k x, right, is equal to LA, right? We're going to say here 9.8. Now put our estimated value of the coefficient of kinetic friction, 0.3. So that's going to be 1 plus 0.3. 1.3x minus 0.3 is the coefficient of kinetic friction times the length, 1.37 equals 1.37a. Okay? So now notice that the acceleration of the object, depends on the portion that's hanging. The more the portion that's hanging, the x is getting larger, the acceleration is actually increasing. You see? So that makes sense. So 9.8, 1.3x minus, and then we do this. So you see, that totally makes sense. As x gets larger, then a is getting larger, as more of it is hanging. So now how do we calculate for time? Okay, we know that acceleration is the rate of change of velocity with respect to time. So there's that t appearing there. The next thing I can do is I can change the differential. I can say 9.8, 1.3x minus 0.411. I can say 1.37. I can make dv dt. I can say dv dx times dx dt. Right? So then I have changed this derivative. Instead of time, I have it with respect to dx. dv dx dx dt. Right? So then I have here 9.8, 1.3x minus 0.411. And then we have dv dx dt is going to be v, right? That's going to be v. So I have here, this is v dv over dx, right? Then I can move the dx over to this side. It gives me a relationship between the velocity and the position x as a function, right? So then I'm going to integrate this, okay? So then I'm going to get 9.8, and then the integral of this 1.3x dx, that's going to be 1.3x squared over 2, right? Minus, right? VdV, the integral of VdV is v squared over 2. It's going to be 0.685 v squared. Then I can divide by 0.685 down here, 0.685. Then I can take the square root of this whole thing. Okay? So that means this gives me a function of v with respect to x, right? Right? Now, do I need a constant there? In my case, the initial velocity was 0 when the value of x was what? And then this one was the portion that was hanging, 0.77 meters, right? So when my value of x was 0.77, the initial velocity of the string was 0. So I need to correct this with a certain constant so that this comes out right. So where does that constant go? Remember when we integrated the function, it was, this one was 1.37 v squared over 2, and then this one was 9.8, 1.3 x squared over 2 minus 0.411, right? So in reality, I should have added a constant here to correct for, when you do an integral, you always add a constant. So that constant I should embed into here, right? And then finally I could put it here, and then I could put it into the square root, right? So then I can say, what should that constant be in order for the velocity, initial velocity to be 0 when the x is equal to 0.77, right? Because that's the initial value of x, 0.77. And if I put here 0.77 for x, the velocity I should be getting 0. So I have, right, plus a constant. So of course this doesn't matter as long as this thing inside of the radical is equal to 0, right? So 0.65, 0.77 squared minus 0.411, 0.77 plus a constant is equal to 0. So it might, okay? So then I can just put that into here, negative 0.0689, okay, into the general function. Negative 0.0689. If all I wanted to calculate was the final velocity of the string, I would put here x is equal to 1.37, because by the time all of it is falling off the table, x will be 1.37. This one will give me the final velocity of the string. So this is a reasonable value, 2.9 meters per second. So by the time it fell off the table, it was going pretty quick. I can calculate the time that this took. In order to calculate time, I need to do one more integral, right? So then I need to say express v as dx dt, right? The rate of change of the position. Then take the t over there, bring the x down here. So we have here square root of 9.8 over 0.685. Then integrate both of this. This will be 0 to t, t being the total time that it took. This one, 0.77 all the way to 1.37, right? The 0.77 is originally hanging, and then the final amount that's completely hanging is 1.37. So this will be a definite integral. This will just be 0 to t. Whatever answer I get over here, I will divide it by this, and that will give me t, right? So let's see what integral that comes out. I can do this on the TI calculator. So this thing is equal to what? 9.8. Okay, so it comes out to be about 0.48 seconds. That's the predicted time that it's going to take for all of the string to fall off. So let's perform that experiment. Okay. This one is kind of hard to measure because it goes by so fast. You'd almost need two people here, one to start it and one to actually perform the experiment, the other one to time it, because it's really going fast. Okay, so you can see here. My experimental time is about 0.6 to 0.7 seconds. I ran it a couple times, but my reaction is kind of slow. There's also other sources of error too, the inconsistency of the coefficient of friction. And remember, when we calculated the coefficient of static friction, we weren't exact with the angle. And we estimated the coefficient of kinetic friction by going down a bit, but we didn't make an exact measurement of the coefficient of kinetic friction. So you can see there's sources of error, but the time I'm getting is a realistic time, 0.5 seconds. And with the reaction time that I have, it's taking a little bit more time, and I'm measuring 0.6 to 0.7. So my error is within reasonable amount. So you can see now how to do this kind of a calculation where it involves quite a bit of integration. You know, how much of the string is going over. And then the acceleration of the string depends on how much of the string is lying over. So you have to take an integral to calculate for velocity in terms of x. Then you have to do one more integral to calculate the position as a function of time. And then you do all the numbers, and then it spits out an answer for the time that it should take. Okay? Thank you very much.